The next type of reaction that we're going to see with carboxylic acids involves amines, and we're going to form amides. The process is actually exactly the same as it was for esters, where we look to remove water. So we're going to remove water in the process of these. I'm going to find my OH from the carboxylic acid, and then take the hydrogen from the amine. So here's my new bond, and instead of making it to oxygen, now I'm going to form a bond to the N. And then anything that was on the N after that is going to come along as well. So this will be NH2. This is my primary amide. So the N is only making one CN bond, so that's why it's primary. Our side product is water. So acetic acid with methylamine, I'm going to find my OH and the hydrogen from the amine, and we'll squeeze those out. My new bond to this nitrogen right here. And on that nitrogen was one CH3 plus a hydrogen. So this is a secondary amide plus water. And then we can do this reaction again. Look for your water, so the OH from the carboxylic acid, the hydrogen from the amine. Here's my new bond. Nitrogen this time has two CH3 groups. So I'm going to draw those. This is a tertiary amide because I have 3 bonds from N to C. And you can write in CH3 if you like, but you don't have to. So whatever is your personal preference there. One molecule that is an amide that you may have used before is DEET, which is N,N-diethyl-M-toluamide, and that is formed in the lab using a carboxylic acid and an amine. So we're going to do the same thing. I find the OH of the carboxylic acid and a hydrogen from the amine and squeeze out the water. There's my new bond. And on this nitrogen, it's a diethylamine, so there's 2 ethyl groups. So this is N,N, diethyl meta-toluamide. Tolu part of that compound comes from the benzene with the CH3, and then we have an amide here, and those are meta to each other. This is abbreviated as DEET. And you may be aware that this is an active ingredient in insect repellents, which is effective against mosquitoes, fleas, and ticks. It doesn't actually kill the insects, it just confuses them. So normally mosquitoes can smell the CO2 that's coming off of you, but when you're wearing DEET, it masks that odor. Once we've formed these esters and amides, there's one reaction that we can do with them, which we've seen previously, which is hydrolysis. Hydrolysis is the introduction of water into a molecule, which usually causes it to revert back to the carboxylic acid. So in each of these reactions, we're going to add water back in. So instead of having the OR here, we're going to put OH in its place. So then I form a carboxylic acid. And our side product is the OR prime plus the H from the water. So these go to form an alcohol. So the OH is going to replace the OR in this reaction. If you will look to see what's being removed, we have an NH2 plus the H. We get a carboxylic acid plus the H and the NH2. So that works with esters and amides as well. Both of those can go back to the carboxylic acid. And here's another reaction with the ester. I have this alcohol. OCH2 is CH3 plus H to form the alcohol. HOCH2CH3. A similar reaction that we can do with esters is something called saponification. So we're introducing water, but now it's under basic conditions. So this is a basic hydrolysis of an ester. And instead of getting a carboxylic acid, we're actually going to get a carboxylate. So we can still remove our water. But now instead of an OH here, that sodium hydroxide is going to pull off that proton, so we're going to get a carboxylate. and then the alcohol. For a saponification reaction, which is how we can make soap, we hydrolyze using sodium hydroxide, and instead of ending up with the carboxylic acid, under the basic conditions, we'll have the carboxylate salt. In this practice problem, aspirin cannot be sold as a liquid solution for children because it slowly undergoes hydrolysis in water. What products are formed when aspirin is hydrolyzed? We're going to do a hydrolysis of an ester, so we have to find our ester. This right here is the carboxylic acid, so we're not going to do anything with that. Our ester is kind of weird here because here's our carbonyl, and then this is the O, and the rest of that is the R. This is our alcohol part. That's going to get released. So our ester part that becomes the carboxylic acid is this part. And then this is our alcohol. So that one's a little bit different than we're normally expecting, because you maybe expected the carboxylic acid part to be the large part of the molecule. What products are formed when both esters in the addictive drug cocaine are hydrolyzed in aqueous acid? Cocaine is obtained from the leaves of the coca plant, which you can see the scientific name of there. So in this one, we're looking to hydrolyze an ester. There's two esters in the molecule. Here is one, and then here is the other one. We'll do one hydrolysis first, and this one's kind of tricky to draw. So this one can get hydrolyzed. And then this one will get hydrolyzed off as well. So there's two there. We're going to add to that this ester. That was removed in the process. So those are the two products that we form when the esters are hydrolyzed. So essentially we've taken this, that was the ester part, and we put an H there. And then on this molecule, this is the part that's getting cleaved off. So if you want to draw that product, there's also an H here with an OCH3. Amides are not very reactive, which is good for us because our bodies are made of proteins which are connected by amide bonds. So if it was easily hydrolyzed, then we would fall apart real easily. So this is a good chemical property for proteins. If you do have an amide, we need to have strong conditions in order to hydrolyze them, and the process is the same. We're going to find our amine that was connected and join it up with a hydrogen to form the carboxylic acid, and our side product with the HCl is actually going to be an amine salt. So it's going to pick up all kinds of hydrogens. All right, you only have to worry about the carboxylic acid part. If you do a saponification with basic conditions, you're still going to circle those up. In this case, you're going to get a carboxylate anion, just like we did previously. So this will be O- with the sodium ion, and then our side product here will be the NH2 plus the hydrogen that we picked up. So for hydrolysis of an amide under acidic conditions, you get a carboxylic acid plus the ammonium salt. And under basic conditions, when you do the saponification, we get a carboxylate anion and an amine. Olestra is a synthetic fat. That means that it was made in the lab. It consists of triacylglycerols, which means that it has 3 ester groups. So if you look at the boxes in gray here, that's showing our esters. They have long carbon chains that can vary between 11 to 19 carbons, and these are found in fats and oils. The metabolism of triacylglycerol involves hydrolysis, which uses enzymes called lipases. So when you're hydrolyzing these esters or the triacylglycerols, We just do our little cleavages here once you find the esters. And one of our products is this 3-carbon chain with the 3 alcohols. This is also known as glycerol. And then whatever R groups were on there will be added to your products as well. And if the R's are the same, then you'll get 3 of the same one. But if you have 3 different R groups, you'll get 3 of these different fatty acids. Once the carboxylic acids are formed, these can be oxidized and converted to carbon dioxide, water, and then energy. If you have an excess of fat consumption, this can lead to all these extra fats being stored in your tissue. So these fake fats like olestra can be used instead. They have lots of esters and they're too crowded to be easily hydrolyzed. So you can see all of the ester groups that are shown here in the arrows. There might be one here. Lots of ester groups. But the molecule is so big and bulky and sticks out a lot that it can't be hydrolyzed. And if it's not hydrolyzed or absorbed, then that equals 0 calories. So those were esters, and now we can look at amides in society. Nylon is made of amides. This is the structure of nylon, specifically nylon 6,6. And we can see all of these amide bonds here in red. Within each of those, there's 4 CH2 groups linked together between the amides. And we might see amides in... So a company called DuPont built the first commercial nylon plant in 1938, and they used that to make parachutes. We may also see nylon used in different products, including rope, fabric, backpacks, hot air balloons, parachutes, and you may also see nylon sutures in medicine. So hot air balloons, sutures, backpacks. We'll also see amides in wool and silk. And these have different connectors in between. So there's only a CH with an R group here, so it's branched versus the 4-carbon linker in between there for nylon 6,6. And when you have these benzene rings here, this makes Kevlar, and you can see the amide bond in gray. So Kevlar, you may know, is used in bulletproof vest. They also use it in a brand of bicycle tire, which is the Armadillo brand. It's reinforced with Kevlar, and it's hard for the sharp objects to pierce these tires, so the cyclists that use them rarely get a flat tire. So with the polyamides, these are many units of amides linked together. We also have polyesters, so you've heard the term polyester before, and now you know the chemical background for it. So this is the structure of polyethylene terephthalate, or PET. So you can see each of those ester bonds there. Those are used in plastic bottles, in mylar balloons, in Dacron, clothing, and other fabrics. And the rigidity of these compounds depends on the type of ester, and also how it's branched. So PET can be used to make knitted material in artificial heart valves, and is also used as a replacement in blood vessels. And we know that some plastic bottles are softer or flexible, just like the water bottles that you may drink for disposable water bottles, versus bottles that hold laundry detergents. There's different plastics. The hardness will depend on the type of branching. We also may see esters in dissolving sutures. If you've ever had to have stitches put in that dissolved, these are formed between glycolic acid and lactic acid to form this ester. And then as your body hydrolyzes these, it just dissolves into your biological systems. There's polymer recycling. Characteristics that make polymers great also make them bad for the environment because they stay around so long. They're built durably, they're strong, and then they don't really react. So there's different varieties. Now, if you've seen these triangles on the bottom of plastic containers, you can see what the material that they're made out of varies. So for number 1, you have polyethylene terephthalate. There's high density PET. Polyvinyl chloride is thicker and it's made from different carbon linker units, etc. So you can see the different types of plastics have different recycling codes. So the lower recycling numbers are easier to recycle. Penicillin is an amide that was discovered in 1928 by Sir Alexander Fleming. That was actually discovered by accident, and he just had stuff growing around his really filthy lab, and at one point noticed that bacteria wasn't growing on a particular plate, and he traced it back to this penicillin structure. So penicillin is made of an amide. There's actually 2 amides. One of them is right here. The other one is a cyclic amide, which is also called a lactam. So we can see that carbonyl with the N there. And penicillin has that characteristic cyclic lactam with the sulfur ring next to it. So there's penicillin G, which you can see the structure of, and amoxicillin is often used if you're allergic to penicillin, and that one has a slightly different functional group here. So instead of having the CH2, you add the NH2 plus the hydroxy, and for people that have allergies to penicillin, they can use amoxicillin.